Okay.
Great, thank you. Okay, so today we're moving forward with this, the main theorem that Alessandro was mentioning at the end of the last lecture, that we can put a derivation on serial numbers, and it's a nice derivation. But let me give a very quick summary of what we've seen, what we have seen so far. So the key thing to remember is the first thing written up here, which is you can see serial numbers as a field of generalized power series with real coefficients here, and the monomials, so the terms you can actually add, which are of different sizes, different orders of magnitude, you can write them as exponentials of purely infinite serial numbers. Okay, because the idea is whenever you take a serial number, if you try to do the exponential of that number, the infinitesimal part, you can treat it using the Taylor series of exp. The finite part is just a real number. You use normal real exponentiation, and on the purely infinite part, where you just create a new monomial when you want to do that. And that's how you construct this huge field, the field of serial numbers. Okay, and then Alessandro defined something more technical. So every time you take serial number and you write it as an infinite sum in these exponential normal forms, you call exponent these gamma i's appearing as exponents of these monomials. Okay, each monomial is the exponential of a pure infinite number, and this pure infinite number is an exponent. And the branch is an iterated sequence of exponents. So you start with some serial number x, and then we call it B0. B1 is some exponent of x. B2 is going to be some exponent of B1, and you continue like that. And the reason for talking about branches was that, for example, you can define this isomorphic copy of the field of transseries that Lau has sort of mentioned during his lectures. And that would be all the serial numbers, actually even in a smaller field, but such that whenever you take a branch starting at that serial number x, then there is a uniform bound on how far you can go along the branch until you hit some iterated logarithms of omega. And actually there's a uniform bound both on how far you have to go in the branch and how many iterations of log you end up hitting. Okay, and that was a key thing. And maybe one thing I want to do before going deeper into derivations, okay, is I want to mention this, how does it compare with the classical construction of transseries? Because I believe that there are quite a few people in the audience who know how to construct transseries from scratch. The classical construction, you start with a generalized power series with real exponents and then you build up. Why do I claim that this T here is the same, is essentially the same, it's isomorphic? Well, this is the skeleton of how you do this verification. So the way you do transseries in the traditional sense would be you start from this Hahn field of power series with real coefficients, and the monomials are just real powers of omega, or if you want, real powers of t minus 1 or of x, any variable, and you do this. So you can do this formally, or what I'm doing this here, I do this inside serial numbers. I can take this. If I start from this field of power series, I can't do exponentials. Here, I can only do exponentials of finite elements, but for the infinite ones, there's no exp of omega because it's going to be bigger than anything here. So the procedure would be to add enough monomials to have all the exponentials of everything here. So you do something, I could call it exponential closure, exponential extension of this one, and you just iterate this. You keep adding exponentials after you do this inductively. At the end, after omega steps, you find yourself with a field which is closed under exponentials. Okay, so you start from this one, you add monomials to get exponentials of everything here, new monomials here, and eventually you're closed under exponentials. But then the exponential function is not surjective because, for example, there is no logarithm of omega here, and by doing exponentials, you won't get it anywhere. So the next step now is to start from essentially the same Hahn field, a Hahn field with real exponents, but now your formal variable, you call it, it's actually log omega, or you call it log of t minus 1 or log of x. And you start from there, you can do the exponential closure in the same way horizontally. And then you notice that if you identify the omega here with the exponential of log omega here, then you can embed this guy into this one diagonally, because this contains the exponential of log omega. And again, the subtle thing is that in surreal numbers, these are actually given. Omega log omega are actual surreal numbers, and doing this exponential closure means literally you take the exponentials. But formally, you can do the same thing by treating omega as a formal variable, as I say here, as a t minus 1. And you define log t minus 1, and you identify the exponential of log t minus 1 here in this extension with t minus 1 here. And you can verify, and that's the technically heavy part in some sense that you have to do, that formally this construction, you can do this construction formally. And then once you have this, you just take the limit here. The direct limit, in the case of serial numbers, this will be just a directed union, because I'm just taking, because in serial numbers, these are just subfields of NO, and so you just take the union of them. And that's how you find this field of transseries. I'm leaving as an exercise to verify that the definition using branches that Alessandro gave last week, of Monday, sorry, gives you the same field that you get by doing this kind of closure and then limit, directed union. And also to verify that if you forget about serial numbers, you can do this from scratch, starting from a formal variable and then doing all the appropriate identifications. I wouldn't say it's easy, but it's it gives you a sense of what's the difference between doing things formally and doing things inside serial numbers. You get the same result, but there's a subtle, more philosophical difference underneath, and also technical. Okay, so this is just to rephrase the context. So we're getting closer and closer to transseries. Okay. Okay, and I'm going to move next. Again, this is going to be, I will have to do the Beamer version of this one, this diagram, but maybe I will just copy and paste the picture in the PDF because it's, because I'm being lazy, I guess. It's a bit, it's trickier to do that in LaTeX. Okay, so now let me move on to the next topic, to the key topic of this course, I would say. This is sort of a central thing, which is a nice property of the field of transseries T is that its theory as a differential field, it's really nice. It's model complete, and so you heard about the intermediate value property for differential polynomials, for example. Okay, so now serial numbers are a much bigger field. So T is contained inside this proper class, which was the closure of real numbers and omega and the sums exp log. It's already a proper class, but this is just a small piece of the entire field of serial numbers. Is there a derivation here, which is nice? Okay, and actually it's going to be an elementary, a model of the same theory. So actually you get the same kind of properties as for transseries. Okay, how do we do this? So the main the theorem that Alessandro stated at the end of the lecture is that on serial numbers, there is a derivation. By derivation, I mean a function with the Leibniz, a linear function, an additive function satisfying the Leibniz rule. So the derivative of the product is, actually I should write this here and realize that maybe reminder is doesn't hurt. So we want this to happen. Delta of x times y must be equal to x delta y plus y delta x. Leibniz Rule. And we want the function to be additive, and that's what we call the derivation. And we can find one with finding a derivation is like trivial, because it's a huge saturated model or a saturated real closed field, so you can put any structure you like. But we can find a derivation such that the derivative of omega is 1. So omega is a kind of representing the identity function. It satisfies the property of H fields. So if you take a positive infinite Surreal number, its derivative is going to be positive. The kernel of the derivation, so the constants, are going to be exactly real numbers. It is compatible with the exponential function. So the derivative of e to f is e to f times the derivative of f. And the hardest property to enforce, whenever you take a summable family of Surreal numbers, then the family of the derivatives is summable, and the derivative of a sum is the same as the sum of the derivatives. This is a strong property. And we want this because it makes sense. It's the same kind of derivation you put on Taylor series when you do formal derivatives of Taylor series. It's the same property satisfied in transseries. So it's the sensible thing you want for this kind of asymptotic expansions. So we want the same here on Surreal numbers. Okay, and yes, and this is an H field, and just a remark, I mean, ST1 and ST2 are precisely, well, they imply that this is an H field. Okay, I won't tell you again what an H field is. It's because I don't need it today. So this is just for reference. Okay, now the challenge is how to find this function. And maybe even, maybe there's going to be also many. Can we find a natural one, one with nice properties? Okay, and then the challenge now is for me to do this, to do most of it is in just in this one lecture. Okay, so we start with, we have a Surreal number, right? And we write it in normal form as a sum of real times the exponential of some purely infinite Surreal number. And I mean, clearly, if I apply ST4 and ST3, I get this is equal to the sum of this is equal to the sum over I of Ri e to gamma I, derivative of gamma I. Okay, it has to be like this because of ST4 plus ST3 as well. So this is an equality. Implicitly, it's also saying that this must be summable. Otherwise, the sum wouldn't even make sense. And well, and now the thing is, I can continue, right? I can iterate this. What if I expand, I write gamma I in normal form? Well, if I do this, I'm going to find myself with something that looks like this. So Ri gamma I, and then for each I get a sum over j of e, I don't know, some real numbers Sij e to eta ij times derivative of eta ij. All right. I just iterated. I do this for gamma I. Of course, each gamma I is going to be a different length. I mean, it's going to be, the j now is running off up to some ordinal beta I. But you get this kind of sum. Okay. And the thing is, I mean, you can continue, right? I mean, I can apply this again. And the rules tells me I must always get the same result. And a thing I could do, and I put a question mark here to say this is something that we need to spell it to make precise. Can I end up with some sum indexed by I, J, K, and maybe I need to, that goes as deep as it needs to, or what? Well, I'm going to see the real coefficient here, all multiplied together. And then all the monomials are going to give me something like this. And then there's going to be something at the end, which I'm going to tell you in a bit what is supposed to be. Okay, so you keep digging into these exponents, and we try to define the derivative as this huge sum of contributions. Okay, that come from navigating and unpacking all these exponents appearing in the exponential normal forms. Okay, so let's try to now to make this a bit more concrete. So I'm going to say first a bit of terminology. Given a serial number, we call these things Ri e to gamma I in the normal form term of x, the serial number. So when I say term of x, I literally mean one of the terms appearing in the Cantor normal form. We say a term is non-constant when it's not in the real numbers, because my target is that the constant field of this derivation is the real numbers. So when I say non-constant, I mean it's not a real. And path is a sequence Pn of non-constant terms such that for all n, if Pn is the term Rn e to gamma n, then Pn plus 1 is a term of gamma n. Okay, so a path is something fairly similar to the branches that Alessandro was using on Monday, but a branch is made of serial numbers, so you start with x. Here a path is made of terms. Why do I want path? Because the idea is that if you look at this expression I was trying to suggest here, these indices I, j, k are describing a sequence of terms, each one appearing in the exponential normal form of the previous exponent. So this term here is a term of gamma I, and this term here is a term of my original number of x. Okay, I see. Is there a message in the chat?
No, I just wanted to observe that a path depends also on the real numbers appearing in the expression, while a branch doesn't depend on the real numbers that appear in the development in the Surreal normal form, no? In the exponential normal form.
Yeah, exactly. So the branch sees the exponent but doesn't know the real number that was attached to it. Instead, the path is the entire thing, real number times e to the exponent. So there is a bit of a so there's a slightly different information in a path that is not in the branch, and that's why we have two different notions, even though they're very similar, because they do different things. And now the other thing I wanted to say is what Christian is asking in the chat. So the path of x, a path of x is a path such that P0 is a term. So it's exactly what Christian was asking in the chat. So let me write actually this. Curly P of X is the set of paths Pn such that P naught is a term of X. Okay. And then when we say path, in general, a path is going to be a path of some surreal number. So it starts with some term and then it continues in this way. Okay, so let me repeat now what is the idea. The idea is that each path contributes something to this derivative here. The derivative of X is a sum, which it's kind of a sum along all the possible paths. So, and the path would be, so the contribution of the path is something like, what do I want to write? Let me put quotation marks for now because this is not a definition yet. So the contribution of the path Pn would be something like P naught times the contribution of the same path but shifted by 1. So you start with P1 rather than P naught. And so you get something like Pk times derivative, the contribution of the path shifted by k plus 1. Okay, I hope I'm not messing up with indices and the plus 1. So this idea is trying to encode whatever was happening in this infinite sum that I was suggesting here. Okay, so let's start now from here. So okay. So we want to construct the derivation by looking at the contributions of all paths. And I was saying there is a problem right here. You keep digging into the exponents. Well, at some point you need to stop, you need to decide what to do. Well, I'm going to give you a vague claim for now. And the vague claim is that most paths enter logarithmic numbers. And by this, I mean that Pn is in lambda no for some n. Okay, so most paths actually become logarithmic along the sequence. Once you're logarithmic, we'll see an example in a moment, you remain logarithmic. So actually the entire path becomes a path of logarithmics, except, I mean, most paths.
Sorry, Vincenzo. So maybe there is a misprint somewhere. I mean, derivative of Pn, you mean derivative of the whole path or just Pn? I mean,
oh, because yeah, the parentheses are, yes. Let me put a index here. So apply.
And then it's P0 times the derivative of P1. Or
no, it's the derivative of P, the sequence Pn plus 1.
Oh, the sequence. Yeah.
Yeah,
okay.
sorry. No,
Yes.
Yeah, it's ambiguous in this way. So I need to. So the sequence is always indexed by n, and I'm shifting the sequence. So you start at P1 instead of at P0.
So this is not really the derivative in the sense that it's a new notion. Derivative of a path is not the derivative.
Yes. Yeah. So each path is giving me a little piece of the full derivative of x. That's what we're trying to do. Okay, and one thing is the path is indexed by natural numbers, so we need to stop somewhere. So I can keep unpacking this product, but most paths end up in a logarithmic. Okay, so we have something to hold on. Okay, sometimes they don't, but when they don't enter.
So sorry, Vincenzo.
Yes.
Just when you say it enter lambda NO as a term or as a as only the exponent part?
No, the term itself. So this is so let me write this a bit. It's slightly more symbolically. That may be slightly less ambiguous. So you take the nth term of the sequence, and this is logatomic. So the term real number times e to exponent, the real number is 1, and the exponent is logatomic.
Thank you.
So the actual product is logatomic, on its own. Okay. And the only paths that don't enter, that don't become logatomic, are small ones in some sense. So we'll see how eventually. And since they're small ones, the point is I'm going to ignore them. I'm going to pretend that they don't exist, and that's going to be fine. It's going to work out. So that's my promise. Okay, so let me give you one concrete example. Suppose that I start with this real number, e to omega plus omega, and this plus omega is in the exponent at the first level. Okay, so the parts of x, there's just 2 of them. So I start with the first term is just x itself, actually, because x is a single term. As a sum, it's a sum indexed by 1. There's only one term. And then I have 2 possibilities. I go to the exponent, and I can choose to pick e to omega, or I can choose to pick omega, because there are 2 terms in the normal form of the exponent. And now, these 2 numbers, I go to the exponent again, e to omega. There's only one term in the exponent, and that's omega. Now, omega is in exponential form e to log omega. Log omega is a monomial, so again, there's only one term in the exponent, and that's log omega, and it continues like this. Then I get 2. The only exponent of log omega is going to be, the exponent of log omega is just log omega, and that's only one term. So I pick that one, and that's it. So I have no choice. And the same happens here. I have 2 paths, and if I want to compute the derivative of x, now I'm going to assume, I know that I want delta omega to be 1, so I can actually unpack this formula. Well, let's see what happens. The derivative of x is going to be exactly the contribution coming from these 2 parts. So the first part is going to give me e to omega plus omega times e to omega times the derivative of omega, which I decide to be 1. And the other part is going to give me this other contribution. Okay, and now you can verify, Leibniz rule, compatibility with x. But this is exactly what you get if you compute the derivation in the normal way, just using the algebraic rules of
Vincenzo,
derivations.
but
yes,
you didn't say how you define the derivative of a path if the path starts with a logatomic.
Yes, not yet.
Okay.
Not yet. No, that's intentional. So
okay.
I want to convince you that this formula is right. It's telling me something right. Okay. So the only thing that actually I need really to do is first to decide the values of the derivatives on the logatomics. So let's start with this piece of information first. So most paths become logatomic. So that's the thing I want to define first. Okay. So let me now shift things around. Oh, no, sorry, not yet. I still want this one to be visible. So the fact is the first observation that we make is that these conditions, SD1, SD4 in the theorem, it doesn't matter which ones they are. They were saying if something is summable, then you can take the sum of the derivatives, compatibility with X. But the axioms that we had, they imply one condition. Whenever you take two positive infinite serial numbers, if the difference between them is infinite as well, then the logarithm of the derivative of X minus the logarithm of the derivative of Y is strictly dominated by X minus Y. Okay. It's a condition. It's an easy exercise to verify that all those axioms imply this condition here. Okay. So now we look at logatomics, and now I define a pre-derivation.
And by the way, this condition is true in every RD field containing log, right? Closed under log.
Yes, right. This is a good point. So SD1, SD4, they're true in Hardy fields. Well, except for derivative of omega is 1, that doesn't make sense. But in the Hardy field, closed under logs, this formula is still true.
Well, the notion of summable families in Hardy field is not so clear.
Yeah. Also it doesn't make sense. I mean, basically, if you have an H field with log and exp, then this is true. Well, log and exp and then the constant field is the reals, the way I've written this. But it's a formal consequence of this couple of rules about from H fields and the compatibility with exp.
Okay.
Yeah. So now I have this, and now I say pre-derivation. I define it to be a map from the logatomic numbers to an O, such that there will be two properties satisfying. Well, at least I want the derivative of exp of lambda to be exp of lambda times the derivative of lambda. So I want the compatibility with exp, and I want condition star.
Sorry, Vincenzo, so which notation do you take? So big D or...
Oh, thank you. Typo here. No, definitely. This is D of e to lambda is equal to e to lambda times D of lambda and the condition star with D in place of delta. And the reason is I want to decide the values on the logatomic numbers. The logatomic numbers have almost no structure. They're just an ordered set, and log and exp are just shifting ground logatomic numbers. They send one logatomic to the other, but the sum of two logatomic numbers is not logatomic, etc. So we can't say much. And now the claim is if I want to get a derivation on the logatomic numbers, I certainly need to have this condition star, and I want this as well. I want this compatibility with exp to be visible, but I can't require anything else. There's no Leibniz rule. There's no additivity because the logatomics have no further structure. So I start with this. I say a pre-derivation is a map like this, and maybe just to show you what the derivation does, I can give you some easy example. Say that I take a logatomic lambda. I take log n of lambda and I apply a pre-derivation. Then by this rule, I know that this is going to must be equal to d of lambda divided by lambda times log of lambda all the way up to log n minus 1 of lambda. Okay, it's just a simple example, and that follows directly from this rule here. Okay. Now my claim is that the pre-derivation is that the basic piece of information that gives me a derivation on all of serial numbers. Okay. How do I work this out? Let's see if I can actually fit. Yes, I can fit the idea and the definition in the same page. So that was done carefully. So let's suppose I have a pre-derivation. And Pn be a path. Okay, and now I define the contribution of this path. And now I want to be more precise, so I'm going to remember this is the contribution coming from the pre-derivation D. So given the pre-derivation D, define what the path gives me. And now the definition goes like this. So the contribution of this path is P naught all the way up to PL minus 1 times pre-derivative of PL if PL is logatomic for some L. So if the path actually becomes logatomic, then I expand, I take this product of all the terms up until I become logatomic, the path becomes logatomic, and then I use the value of the pre-derivation here, and I plug it here. Okay, why this? Because I remind you, the idea was each path, the contribution of each path should be something like this. It's the product of the terms in the path all the way up to some value that I need to fix. And now that I have the logatomics, I decide the values on the logatomics, I can use it to give meaning to define this value here. Okay, and then I define this to be 0 if there is no such L. Okay. Any objections to this definition?
What might happen if you don't plug 0?
Yeah, that's a beautiful question. I think you can put something else here, and that would be fine as long as you put values which are small, so they must be in the right place. But there is no. I mean, I don't think that anybody has worked out one explicit example where you can do this. So yeah, so it's not forced. So this is not necessary. It's not necessary to put 0 here. You could, in principle, put something else. But for simplicity, we go for the easiest route and we put 0.
So, sorry, Vincenzo, I didn't get. So
yeah,
are you saying that you could have chosen anything else than 0? Or
well, not quite anything. In the end, I want this condition star to be
right. Mm-hmm.
So star, but actually I want even more, right? In the general setting. So the final derivation I want it to satisfy to be an H field, and that gives me restrictions.
Yes.
But the restrictions are all about the size of this element.
Okay.
And they're not much about. Well.
Okay. I see.
But with 0 it works. If it's non-zero, nobody knows really, right?
Yeah, exactly. So we know that there are restrictions, but other than that, I'm fairly convinced that you can put some value there as long as it fits in the right place. It's in the right cut.
I think that I thought a little bit about this, and the natural solution would be to do the product of all PIs, because those paths must be infinite, right? So you can do the transfinite product of all PIs, but then you have to define product of real numbers, transfinite product of plus and minus ones, and
this
requires some choice. So
Yeah, the thing I didn't say is that the real numbers become plus minus 1. So that takes care of some of it. But then there's a deeper issue of you don't know whether this is going to be positive or negative. That might be a challenge. Okay, I think we're getting deeper. Maybe we can. I think that this is more material for Q&A to speculate on this.
Right, I agree. Sorry for my question, actually. Okay.
No, it's a good question. I mean, I think there's a question in the chat from Christian, which is in the similar spirit. Like, if I plug 0 here, how do I know that actually that this is non-zero? You know, that maybe I'm putting too many things to 0. But then again, my claim that most paths become logatomic is relevant here. So actually, there's always going to be some non-zero contribution unless you started from a real number, and then you get exactly this condition SD2 that the kernel is precisely the reals. But this is not, I mean, it's not obvious. At this point, I haven't given enough details to see why this is happening. So we get there. Okay, so I gave you this definition, easy exercise. Oh, sorry, I didn't finish the definition. Once I define the contribution of a path, I define derivative of x to be the sum over all the paths of x of these contributions. Okay, and I'm using a non-optimal notation. So the paths are sequences, and I apply this delta d to each sequence, and then I take the sum of all of them. And we call this the derivation induced by x. Sorry, derivation induced by d. Okay, and this definition is a claim already. The claim that there are two implicit claims. One is that this is a summable family, and the other is that this is a derivation. Okay, I'm going to leave as an exercise that this is a derivation. So that delta of x plus y is equal to delta of x plus delta of y, and that delta of e to x is equal to ex times delta of x. This is enough already to show that the Leibniz rule holds. Okay, so very briefly, because what's happening here, if I take x plus y, you can see that unless there is cancellation, but let's pretend to be working in a very simple situation, the path of x plus y are going to be the path of x and the path of y. Because a path is just a sequence of terms starting with the term of x plus y. And the terms of x plus y are, in the generic case, the terms of x and the terms of y. It becomes a bit more complicated if the same term or the same term, but with almost the same term, but with different coefficients appears on both sides, in both x and y. And then you have to sum them together. But it's algebraically, you can verify this fairly easily that there is an equality here. So this is left as an exercise. And this one is a bit more obvious. I mean, in the special case where gamma is purely infinite. So if this is a monomial, you can see that this is coming almost directly from the way we define the contribution of a path. Every path is going to start with in e to x, and the contribution of a path is always e to x times the contribution of the shifted path. So the path starting in the exponent rather than in the original number. And you can verify a formula like this. But I'm not going to prove it. I told you enough already. So the principle is you get the derivation, it's compatible with exp. What it's missing is one, that it's actually well defined, and B, that it's an H field, that it satisfies also SD1, for example. Okay, so again, first, we still have two ingredients. first we need to figure out, we want to build a pre-derivation. So is there an actual pre-derivation anywhere? And the answer is yes. So let me move this down to, so that we have the definitions in place. Up to here. So yes, there is a pre-derivation of serial numbers, and also there is a simplest, there is a canonical one. Simplest. So I'm not going to say what is simplest, but it's kind of like, it's similar to the way the sum is the simplest function that is increasing in both arguments. And the simplest pre-derivation is the same thing. It's you can define it inductively in a similar way. Okay, and we have an explicit formula, so I can actually give you the value of this pre-derivation. A posteriori, I mean, if you knew the value from the start, then probably we would have had an easier life when we were trying to do this. So the derivative, the pre-derivation of lambda, logarithmic lambda, is the product of the logarithm of lambda, okay, finite logarithms, log 1, so lambda, log lambda, raw natural numbers, divided by the product over alpha, and I'll tell you what alpha is, of the alpha logarithm of omega. Okay, I need to give you a couple of definitions. I mean, this log alpha omega is just a suggestive way of writing the log-atomic number lambda minus alpha. Okay, minus alpha is a serial number. You plug it in this lambda x, this function covering all log-atomic numbers, and I take this one. And alphas are the ones such that there exists an n such that log alpha omega is greater than or equal to logarithm n times of lambda. Okay, these are the ones that you put in the denominator. And that's it. I mean, this function is the simplest in an appropriate sense pre-derivation you can put on log-atomic numbers. I won't prove it. Rather, I want to show you at least this formula, what it does. So take a log-atomic number, for example, which is greater than any iterations of exp of omega. In this particular case, no matter how many times you apply log to lambda, you're never going to see, what you find is always greater than omega. So certainly you're not going to see any contribution from this denominator, from these guys here. So what is left in this case is just a numerator. And so the lambda is just the product for n less than omega of log n of lambda. So let me spell this out clearly to show you where it starts. It's like this, it's lambda times log lambda, etc. And it's exactly this product. And it's an infinite product in the sense that Alessandro defined on Monday again. Okay, when lambda is equal to omega, now something different happens. I do the omega. Well, the numerator is the product of the logarithms of omega. The denominator is what? So what are the ordinals alpha such that log alpha omega is greater than log n omega for some natural number? Well, it turns out it's exactly the same. So let me say alpha here so that, oh my, losing valuable seconds here. The denominator you computed is just this one, and actually this is just 1. So the derivative of omega is 1. This was not baked in the definition of the pre-derivation. It's just that the simplest one does this, which is what we want. And then when I plug lambda equal to this log beta of omega, then this is also a nice calculation to do. D of lambda is, at the numerator, I get the product of a natural number of log beta plus n of omega, because of the formulas, again, that Alessandro mentioned on Monday about this function lambda. You get precisely log beta plus n. And at the numerator, you can verify the alphas that appear are precisely the alphas less than beta plus omega. And, well, if you work it out, lots of things, some things cancel out, and you're left precisely with 1 over all the iterated logarithms of omega just for alpha less than beta, which if you plug a natural number here, then you recognize the usual formula for the derivative of the iterated logarithms of omega, of just x. You get 1 over x times log log x, all the way up to n minus 1.
So sorry, so in your notation here, so alpha or beta are what exactly? What
ordinals,
type of
ordinals,
they both are ordinals.
ordinals.
Okay, thank you.
Thank you. Oh yeah. This is quite a yes. No, this is an excellent point, and without it, it wouldn't work. This would be a huge product otherwise.
Okay, thank you.
Yeah. Okay. Now the theorem with which I have to end is that the family, so for this pre-derivation, this particular D, the family of contributions, the path of some x is summable, which means that the derivations induced by D is well defined, and the derivation, the induced delta, satisfies SD1, SD4. So you do get a derivation, and you do get the property that we wanted, which are far away now. So let me go back to, there it is. So this derivation, delta omega is 1, and we can see this directly from here because the pre-derivation is value 1. And delta is going to agree with the pre-derivation of the logarithmic numbers. And the other one are less obvious. As Christian was asking, this property that x greater than r implies delta of x greater than 0. It's not hard to prove. So we should see this. But there's already a deeper reason for it. I mean, and the reason I can tell you in words right now is that whenever you take x, there's going to be a path which is bigger, quotation marks, than all the other ones. And it's the path that if you take, what to do is you take the largest term of x, which means the term with the largest monomial. The coefficients may be positive or negative, but you look just at the absolute value. And then you take, in the exponent, you take the leading term, and then you continue like that. And this path, in some sense, is bigger than all the others, and you're going to see that its contribution is strictly dominates the contributions of all the other paths. And so that tells you whether something is positive, negative, or 0. You can see it from there. Okay. Now, yeah, Sigrid is asking, can D be any pre-derivation? No, actually. No. So this theorem, we stated this for this pre-derivation here. And our proof, the way it's written, it's automatically true whenever the values of the pre-derivation are terms. So there must be monomials, maybe monomials times a real number. But then there is a more general family, a pre-derivation. It can take values in some real numbers, but then there is an extra summability condition that I don't want to write here. So there is an extra condition that you need to. So this theorem applies to all the pre-derivations satisfying something else, and the something else is necessary and sufficient. So these are precisely. So we can give a general statement here. I just don't want to do this now. Okay.
So notice
yes.
that this simplest pre-derivation takes values in the monomials, right?
Yes, because the point is, in this particular case, this value is a monomial. It's a product of monomials, and an infinite product of monomials is a monomial as well. So it's so in this case is easy. There is a more technical thing that you can say when the derivation doesn't take value in the monomials. It's an extra.
But whenever
extra
it takes
function.
values in the monomials, it works. It's you get the summability and everything, right?
Yes.
And
so
also more
let
generally.
me write this here. So for the simplest D, this is true. Also for every pre-derivation such that the image of the pre-derivation is contained in omega or even terms, real number time monomial. So that's a formal statement I'm happy to put on the screen. Okay, I think I have to stop, right? I'm happy to answer questions, but the lecture should be
Thank you.
stopped here.
Thank you. I stopped the recording.
Thanks.